Here's another one. This one should be pretty quick. Several people are in a building with several rooms. Each minute, one person leaves a room and moves to another that has more people, not counting the person moving in it. So, just to make this clearer, a person in a room with A other people can move into a room with B people if B is bigger than A. Prove that eventually all of the people will end up in the same room. This is a nice little model of what's happening when you have breakout rooms in a Zoom class and everybody can move around. And let me just do an example. So I'm gonna encode a state as a tuple. So when I say 4 to 2, I mean there is 4 people in one room, 2 people in another room, and 2 people in a third room. So what can happen? Nobody from the first room can move into the second room because this B greater than A condition is not satisfied. However, for example, one person from this room can move into this room because this room has 2 people and this room has only one other person. Keep in mind, A is the number of other people, not the people moving, that he doesn't count himself. So one thing that can happen is that one person from this room moves into that room. What can happen next? For example, one person from here can move to here, or one person from here can move to here. There is no determinism here, so there is many possible options in most choices. So let's say one person from here moves to here, so we get 5, 1, 2. Then this remaining holdout moves from the second room into the third room, for example. The second room is now empty, we could basically ignore it. I'm just gonna throw it away now. And now nobody from the big room can move into the small room, but people can move from the small room into the big room. And that's it, everybody's in the same room now. All we need to explain is why this happens always, not just for this particular state and for this particular sequence of moves. And again, as with most such problems, a monovariant comes helpful. Namely, define the dispersion of a state to be the number of pairs of people that are in different rooms. Really, it makes sense to say unordered pairs of people, but even if you do ordered pairs, that just multiplies the number with 2. It doesn't really change anything we care about, so we can just use ordered pairs. So this is a non-negative integer. Now I claim that each move decreases the dispersion. Indeed, if a room, so I'm just gonna copy the definition of a move here. If a person in a room with A other people moves into a room with B people, where B is bigger than A, that's the requirement for a move, then the dispersion, I claim that it decreases. And I claim specifically that it decreases by B minus A. So this now, of course, you have to make it clear whether the pairs are ordered or not. Let me make them unordered. What happens? This person and those B people, they were in different rooms, so we had B pairs of people in different rooms that now disappear because that person now moves together with those B people. Whereas we had the pairs consisting of the moving person and the A people whom he moves away from, those pairs now start contributing to the dispersion. So really the dispersion decreases by B and increases by A, but this is just saying it decreases by B minus A. This means it decreases because B minus A is positive. And that's because B is bigger than A. Thus, the dispersion decreases every minute, but it cannot keep decreasing forever, since it is it has to remain a non-negative integer. So the moves must stop. And what does this mean, that the moves must stop? It means that there are no more two people, there is nobody that can move anymore. So we achieve a state in which no one can move anymore. However, if you have two different rooms with at least one person in each, then there is always somebody who can move. So if nobody can move, this means that all the people are in the same room. So just to make this clearer, if you have a room with A people and a room with B people, one of them is at least as large as the other, and then the people, anybody from in the smaller room can move into the larger room. You can check it. So if nobody can move, then there are no two inhabited rooms anymore. So everybody's in the same room, and that's exactly what we wanted.